let us come to Q derivatives. We have done U derivatives, alpha derivative, alpha dot derivative, now Q derivatives. Okay, again we start like f(a)x, f(a)z and m(a). Why we are taking these three things? Please understand, we are trying to build longitudinal perturbed equation of motion. And these things we are doing to find out the perturbed forces when the aircraft is perturbed in the longitudinal mode, that is either this or pitching motion. That is why f(a)x, f(a)z and m(a) are being considered. Okay. So, I can easily write f(a)x is equal to qs cx. So, df(a)x by dqc by 2u1 will be equal to q1 bar s dcx by dqc by 2u1. This 1 again because you have to evaluate this at steady state. Okay. So, this I can write as cxq into q1 s. It goes without saying, cxq means dcx by dqc by 2u1. And for small angle, you can assume that is minus cdq, because you know the axis system what we are using, x is in this direction, however, drag will be in the opposite direction. So, they are minus sign. And then another relief for us, generally CDQ is very negligible, so we will take it as 0. Please understand, these assumptions are no way restricting you to use finite value and go for complete analysis. Okay? Now, we will handle f as z, and we again write f as z as qs cz and df az by dq c by 2u1 is equal to, evaluated at steady state, equal to dcz dqc by 2u1 into q1s. The catch point is how to evaluate dcz by dqc 2u1. Now, let us see what is actually happening. Suppose this is the tail, okay, and this is the CG of the airplane, and if it is going for a Q, pitch up like this, what will happen? This man will go down, tail will go down. As it goes down, there are relative air speed it will see, and roughly I can say delta alpha equal to Q LT by U1. I am saying this is from AC, it is LT. I am assuming the net force is acting represented at the AC of the tail. And this delta alpha will give lift at tail. Also, it will give moment due to tail about CG, because for us moment about CG is extremely important for analyzing its response. Right. With this understanding, we have a clear-cut indication that this is one of the important derivatives. So, let us evaluate this. You can see yourself, I can write dfaz by dqc by 2u1 is equal to minus dcl by dqc by 2u1 into q1s. How do I write this? Because I know it is fair enough assumption Cz equal to minus Cl when we are talking about small perturbation. Right. So, dCz by dqc by 2u1 is minus dCl by dqc by 2u1, or this is by notation is written as minus Clq with q1s. The question comes, can we derive the expression for Clq? Answer is very obvious. because we know the mechanism how this Cl comes because of Q, it comes through delta alpha. So, it should be very straightforward for us, and let us find out the expression for CLQ. Please understand CLQ could be because of CLQ tail, then because of CLQ wing, and also fuselage and other components, but we are mostly convinced that CLQ tail will be predominant. So, we will try to derive expression for CLQ tail. Right. So, we know that delta alpha tail because of Q is Q LT by U1, which we have demonstrated here. Right. So, what is the CL at the tail? Will be CL alpha tail into Q LT by U1. So, what is lift at the tail because of Q due to Q will be equal to half rho V square at tail S tail into CL tail, which is CL alpha tail into Q C by 2 U1. If you want to find out CL based on free stream dynamic pressure, then this will be half rho V square tail into S tail CL alpha tail Q LT by 2 U1 divided by half rho V square S free stream, that is all. And you know half rho V square tail by half rho V square free stream is neta. So, I can write CL tail because of Q as CL alpha tail into neta, this is neta, then ST LT by S, right, ST LT by S, then Q by 2 U1, okay. CL alpha half rho V square by this is neta, and then here will be LT by C. No, there is no C, so this will be LT. So, let me check again. Half rho V square tail by half rho V square free stream is neta. Neta is here. CL alpha tail, yes, it is here. Q LT by 2 U1 is here. Everything is here. S is also here, but S is nothing but S of the wing. Generally, we use that. And if I want to find out CLQ, which is dCl by dQc by 2 U1, best way to find out CLQ is simply divide this by QC by 2 U1 because they are linear, QLT by 2 U1 divided by QC by 2 U1. No, there this one won't be 2, right? Please understand, this will not be 2, this will be QLT by U1. That is a mistake from my side. CL alpha tail into QC by U1. I repeat, lift due to Q with half rho V square tail ST CL alpha tail into alpha. This alpha is nothing but QLT by U1. Okay, so there was a mistake here. So you correct it. So CL will be, the CL is based on aircraft reference and based on free stream dynamic pressure. So I divide by half rho V square free stream into S. So this to this is neta ST CL alpha tail QLT by U1, and once I want to find out CLQ, so this 2 is not here. So I divide it by this, and then I get an expression which is very well known, which I have done in my last course also. You can refer to that. So I will get a CLQ expression as 2 CL alpha tail into neta tail VH. That is all. You see here. If I do this, this get cancelled, U1, E1 get cancelled, this 2 goes up. So 2 CL alpha tail, neta T is here, ST LT by S, this C bar makes it VH. So VH is here. So this is the expression for CLQ. note that sign of CLQ is positive, which is true because as it goes pitch up, it pushes the air down, so that lift is upward. But then the question is that CLQ will give a nose down moment, which is negative. And how do I find that? Very simple. I multiply this with tail moment term. So, from here I write CMQ will be 2 CL alpha tail neta t VH into LT by C. But I will be wrong if I do not take care of the sign, because I know because of Q there will be a force upward, which will give me a nose down moment. So, I have to put minus sign here. But as I told you, this is the expression for a contribution by tail. But generally, wing also will contribute, fuselage also will contribute. So, you can roughly as a design stage, you can take CMQ as minus 2.2 CL alpha tail neta t VH LT by C. This is also very recommended value or expression at design stage. Please understand this. So, we know the expression of CLQ and CMQ. We derive this expression just to convince you that although they look very nasty, but very simple to estimate. I know CL alpha tail, I know ratio of the dynamic pressure, maybe 0.9, 0.95. I know tail volume ratio. What is the problem? I can find out this derivatives, right? As a designer, you always associate all these derivatives through numbers. Unless you develop that feel, you are not ready for designing an aircraft. So, typical value of CLQ you will find it will be between 10 to 80, 15, and CMQ also could be minus 10 to minus 20, around these typical values for CLQ and CMQ. Now, what we are left with the delta E derivative, right. So, let us see that also, so that we are out of all these expressions, and because our main aim is to go back to this equation and try to understand the short period equation of motions in terms of how to solve them, how to get useful informations. These are only we are creating input for solving those equations, right. Again, we start with, because longitudinal we are talking about FAX, FAZ and MA. I will go very straight dFAX by d delta E, I will write as dCx by d delta E into Q1 S, which I can write as Cx delta E into Q1 S, which is nothing but minus CD1 Q1 S, because minus CD1 minus CD delta E evaluated at steady state the Q1 S. What is the physical meaning of CD delta E? See, whenever you deflect the elevator, right, definitely there is going to be change in lift as well as drag, and that is CD delta E is reflecting. And that is why when you try to trim an aircraft at a most optimal altitude where mostly you will be flying, you ensure that the elevator deflection is almost 0. That is, you design your aircraft such a way that your CM versus CL graph look like this, and this is your trim point for delta E equal to 0. Right. So that your this contribution to drag is 0. Similarly, if I want to find dFAZ by d delta E, this will be dCz by d delta E Q1 S. It goes without saying 1 means steady state, because these are to be evaluated at steady state, and I am sure you understand this is equal to Cz delta E into Q1 S, and this is minus Cl delta E into Q1 S, because Cz and Cl are opposite sign for small perturbations. And what is CL delta E? You know, if I deflect elevator, how much it will generate CL, right. So, these are not very difficult thing. Similarly, if I write dm by d delta E, this will be dcm by d delta E into q1 s c bar, and this is very popular, very strong derivative Cm delta E Q1S. And what is Cm delta E? You know, it is the elevator control power. Okay? And we have already derived those expression in last module. It is the elevator control power, and typical value is minus 0.7 to 1.5 per radian. So, that completes this derivation of all those derivatives which will be required to solve longitudinal perturbed equations of motion. My strong advice would be, please spend some time with pen and pencil, and you can also refer my last course, where also I have talked about this, but in this course the objective is different. I may be going a little faster because this is not primary objective. Primary objective is to build a dynamic stability criteria so that we can design a stability augmentation system. Right? So, those who are interested, please follow that module also and derive this expression yourself once, and you need to do it once only, that is all. After that, you remember the formula, note down at some worksheet, whenever required, refer it, calculate it, and done with it. Okay?